pi dl cross r divided by r cube. Okay, so mu is the permeability of the medium. Okay, so here we are considering current carrying wire, so that will induce the magnetic field, and in this Beard-Savart law we are finding strength of the magnetic field at any arbitrary point. So this is the formula you studied in the electromagnetism, maybe in the physics. So we have to use this, we are going to use this, so for our aerodynamics. So they converted like this. So instead of the current carrying wire, they are applying this Beard-Savart law for the vortex filament. Okay, so instead of the wire, they are considering the vortex filament, and instead of the current, here we have the strength of the vortex filament, capital gamma. Okay, and vortex filament means this is how the vortices are formed around it. Okay, and here we are going to find velocity induced at some arbitrary point due to this vortex filament. Okay, so there we consider current carrying wire, and we consider strength of the magnetic field. So here we have vortex filament. Instead of magnetic field, here we have vortex, and here we are finding velocity induced by that vortex. So they are rewriting the formula. So dV is equal to gamma divided by 4 pi, same dLr divided by r cube. Previously it was dB is equal to mu I. Okay, these two terms are changed. Instead we are having dV and gamma. So they rewritten this formula for the vortex filament. So now we can further simplify this. So here the arbitrary point is between the two ends. Here the arbitrary point is just opposite to the fixed end. These are all the 4 cases we are discussing. This they may ask in 12 marks, 4 different cases. Okay, or they may ask each cases in the 4 marks. They may ask vortex induced, the velocity induced by the finite length vortex filament, or semi-infinite length vortex filament, or infinite length vortex filament. Like that, they may ask these things in the 4 mark. So this is the equation we got it from the Beard-Savart law. So from this we are going to proceed for the first finite length vortex filament. So here I am taking finite length vortex filament. See, both ends are finite. It is not extended to the infinity. So initially I am taking one small distance on this vortex filament dl, and this dl induces the velocity at some arbitrary point dv. Okay, I am taking this distance is r, and this inclination is theta. Okay, so randomly I am taking one small distance dl, which induces the velocity dv at some arbitrary point. I am taking the distance between that area and the point is r, inclination is theta. Then I am drawing one perpendicular line to the vortex filament that I am taking as h. Okay, so this is the perpendicular line that I am taking as h. Okay, so this formula just now we derived gamma divided by 4 pi sin theta by r square dl. Now I am going to apply this to this finite length. Okay, so this dv is induced by this small length dl, and if you want to find the velocity induced by the complete vortex filament, then we have to integrate it. The same equation we have to integrate it and limit. So normally what we will take, the limit varies from 0 to L, but in the potential flow everywhere we are taking in terms of theta. Okay, so instead of 0 to L, here we are taking in terms of theta. So to convert the theta, we are joining this 2 end with the arbitrary point. Okay, this B point I am joining with the arbitrary point P. So I am getting the angle beta. So always I am measuring the angle in the clockwise direction. So this angle is beta. Similarly here also A point I am joining with arbitrary point P. Here also I am measuring the angle from clockwise direction, it is alpha. Now I can integrate it for these two thetas. So integral alpha to beta gamma by 4 pi r square sin theta dl. Same equation, just integration I added. Is that clear? First bench. Any doubt? You can ask me. You can ask me, I will repeat it if you want. So I repeat, I am taking finite length vortex filament. Initially, I am taking small distance, which induces the velocity dv. So distance between that area and the point is r. Inclination is theta. Then draw one perpendicular line that I am taking as h. And to apply the limit, I am joining this P point to the P. Then A to this P. I am getting two angles. This is beta. This is alpha. So instead of 0 to L, I am taking alpha and beta, because everywhere in the potential flow we are taking in terms of theta. So this is the first equation. Now if I have to convert all the terms into theta, so I don't want this R and dl. So these two terms I have to convert in terms of theta, then only I can do the integration. So for that I am taking this right angle triangle. So here I have taken same thing. Okay. So this formula just now is discussed, integral alpha to beta, this value. So using this right angle triangle, I can write sine theta, which is h by r, and tan theta, which is h by l. So I have to convert this r. So from this I can write the r equation, r is equal to h by sine theta. And from this tan theta, I can write this dl. So first I am writing in terms of l. So if you rearrange, you will get L is equal to h by tan theta, that I can write it as h cot theta. Okay, so from this right angle triangle, I am converting R and L. But what I need is the DL, then differentiate, you will get DL is equal to cot theta. If you differentiate, you will get minus cosecant square theta. So minus cosecant square theta d theta. So this also I can modify. Instead of cosecant square, I can write 1 by sine square. So I don't want this R and DL. So I am taking this right angle triangle to convert R and L to the theta. Okay, sine theta, tan theta. Using that, convert R and L in terms of thetas. Okay, these two terms. Now I am going to substitute in this R and DL. Okay, so instead of R square, I have substituted sine square by h square. Instead of this DL, I have substituted h divided by sine square. So minus is outside. Now simplify, sine square cancel. The remaining you will get this term. Okay, and integration of sine theta you will get minus cos theta. Outside another minus is there, so it is plus. So you will get gamma divided by 4 pi h cos theta limit alpha to beta. Okay, and if you apply the limit, you will get cos beta minus cos alpha. Up to this for the finite length. So if you know this theta, we can find the velocity induced by the finite length vortex filament. Is that clear? So same equation, I just write it in the integration form so that I can find it velocity induced by the complete vortex filament. Then convert R and DL using this right angle triangle. So simplify, you will get finally this equation. Actually, this Biot-Savart law, so the original law itself, we are finding the magnitude. Okay, so we don't care whether it is positive or negative. We are finding only the magnitude of the strain. Here we are finding magnitude of the velocity. Even though if you are getting some negative term in the equation, you don't need to worry, because finally what we need is the magnitude. That's it. This is the first case. Okay, this is for finite length vortex filament. This is on 4 mark. And remaining cases, it is very easy. So this is the base equation now. From this straight away, we will find only alpha, beta for different cases, and we will find it. Okay, only this is little bigger, this derivation. Other things are very easy. Okay, this is the second case, semi-infinite vortex filament. Okay, now to convert this finite into semi-infinite, I am extending one point to the infinity. So I am taking this B point to the infinity. So if I take this B point to the infinity, then this beta will be 180. Do you agree? because see here, this is the finite length vortex filament. This B point, I'm extending to the infinity. That is, this is the B point. I'm extending this to the infinity. So if I extend this point, you see, previously this is the beta. Now when I extend, see the beta is increasing. And if it goes to infinity, finally I will get a straight line. So angle will be 180. Is that clear? Okay. So if the point goes to infinity, beta also will increase. So finally for infinity, I will get 180 degree. So alpha is finite, beta is 180. Substitute here. So alpha is same. Only beta I am substituting 180. So cos 180 is minus 1. Take minus 1 outside. It is a modulus. So I am not taking the minus. So finally I will get gamma divided by 4 pi h 1 plus cos theta. So this is another one 4 mark. Stand up. So in the 4 mark, if they ask, stand up. So straight away you can write this equation. You can substitute beta is equal to 180. You can write this step. Only 2 steps, but this diagram is compulsory for 4 marks. Okay. So no need to derive this previous things and all. Sometimes if they ask, so state the Biot-Savart law and find the velocity induced by the semi-infinite vortex filament. So then you have to write, you can write this equation, Biot-Savart law, you can explain. So we are finding the velocity induced by the vortex of the vortex filament. Then you can write these 2 steps, these 2 steps, this diagram for 4 marks, if they ask. Or if they straight away ask, write the velocity induced by the semi-infinite, only this diagram, then these 2 steps, that is sufficient. Okay, so this diagram, these 2 steps are sufficient for 4 marks. This clear, right? Semi-infinite. Then third one, so this is the second case. Third case, we are taking infinite length. That is, both ends are go to infinity. Okay. So both ends I am taking to infinity. So this already we discussed. If this point goes to infinity, then beta will be 180. And if this A point goes to infinity, then this angle will be decreasing. If you keep on increasing the distance, finally it will be 0 degree. Okay. So substitute beta is 180, alpha is 0. You will get minus 1, minus 1, totally minus 2. This is modulus, so cancel the minus. Remaining you will get gamma divided by 2 pi h. This is one 4 mark. Okay, so this diagram, write alpha, beta values. So substitute here, you will get gamma divided by 2 pi h. Sometimes they will ask in 1 mark also. Okay, they will give 4 choices. So gamma divided by 4 pi h, gamma divided by 2 pi h, like that they will give 4 options. You have to memorize, no other way. Or if you can remember this formula, by remembering this diagram, you can find. Okay, so 3 cases we discussed: finite, semi-infinite, then infinite. Then special case of semi-infinite. So previously, so one end is fixed, one end goes to infinity. The point is between the 2 ends. Okay. And in this case, same semi-infinite, one end goes to infinity, one end is fixed, but the arbitrary point is just opposite to that, so fixed end. Okay. So in this case, the arbitrary point is just opposite to the fixed end. So beta is 180. So if it is just opposite to the fixed end, then this is 90 degree. So this is 180, this is 90. You will get minus 1, minus 0. Then finally gamma divided by 4 pi h. Okay, 4 cases. So finite means gamma divided by 4 pi h cos beta minus cos alpha. Then semi-infinite. So this is 180, so 1 plus cos alpha. Then infinite. So both are 1. You will get gamma divided by 2 pi h. Special case of semi-infinite. That is 90 degrees, it is 0. So we are getting only gamma divided by 4 pi h. That's it. Savatla, 12 marks. Okay, so if they ask all the 4 cases, wherever possible, you can simplify the steps. Sir, clear? Savatla. Okay. So next one. So next one is I am going to compare. So lift produced by the aerofoil and wing. So what do you think? Will it be same? For example, so I am having NACA 24 into aerofoil. Okay. At 8 degree, it is giving CL of 1. Okay, NACA 24 into aerofoil. For 8 degree, I am getting CL is 1. Now I am making the wing using the same NACA 24 into just straight rectangular wing. I am keeping same angle 8 degree. Now what will be the lift? Will it be same or decreased or increased? Any guess? Just guess. Question now. So I am using NACA 24 into aerofoil. Angle of attack is 8 degree. So I am getting corresponding CL is 1. Now using the same aerofoil, I am creating one wing, just straight rectangular wing. So this also NACA 24 into everywhere. I am maintaining the same angle of attack. Now what will be the lift? Will I get same 1 or less than 1 or greater than 1? Less than 1. So we will get less than 1. So we won't get the same CL for wing. Always aerofoil will have maximum CL. Wing will have less CL. Straight away we'll go to the graph once. This is for the 2D wing. That is 2D aerofoil. This is for 3D wing. Even though if you use the same aerofoil, the curve will be less. At every angle of attack, for example, this is angle of attack 8 degree. Aerofoil producing CL of 1, but the 3D wing may produce only 0.6 or 0.7. Okay. So now let me explain the reason. So this we already discussed. So if you take a finite wing in the flow field, there will be a side leakage flow, then there will be a wing tip vortices on both sides. Okay. So this is the rear view. This is how the vortices are moving. Okay. So inside, so all those vortices facing downwards. That is why we are getting the downwash. That is downwash means just flow in the downward direction. That's it. Okay. So there are vortices on both sides, which is rotating in this direction, clockwise direction. So outside, I'm getting upward components. Inside, I'm getting downward components. This downward component of the flow I'm calling as downwash. And both outer side, I'm having upward component that I'm calling as upwash. So this upwash already we discussed. Whatever the wing that is birds are flying next to it, it will get the additional push. Okay, so upwash already we discussed what is the benefit. But if you see this downwash, so it is affecting the performance of the wing. Okay, so the upwash is beneficial, but it is not acting on this wing. It may be beneficial only to the other wings which is flying next to it. Okay, so we no need to worry about this upwash. If we are finding the aerodynamic property of this wing, then we have to worry about only this downwash because this affects the performance. Okay, and the downwash, this is how it affects. It is not only active, that is acting on the rearward, it is acting on the wing also up to certain upstream portion. See, this is the downwash profile. Okay, some vertical component from the top. So it is not only in the rear portion, it is also acting on the wing, also in the front portion. So because of this front portion and acting on the wing model, what happened? Assume this is the aerofoil. This is the flow direction, horizontal, and angle of attack is always measured between free stream flow direction and the chord length. Okay, assume this is 8 degree. And I'm creating a wing using this aerofoil. If it is the wing, then there will be a downwash. Downwash means downward component of the flow. So what will happen? This downward component of the flow, it is acting rearward on the wing, also in the upstream portion. So what happens? This downward component of the flow deflect the free stream flow. Actually, it is straight, but because of the downwash, it is deflected downward. Now, if you find the angle of attack, you see, now this is the flow components. Now we have to measure angle of attack here, because definition of angle of attack is angle between free stream and the chord line. So previously it was horizontal, so we have taken this alpha. Okay. Previously it is horizontal, so we have taken this alpha, but now due to the downwash, it is deflected. Now this is our resultant flow component. Now the angle of attack is reduced to this much. So as alpha increases, CL also decreasing for the wing. Okay, so due to the wing tip vortices, there is a downwash. So downwash affects the upstream flow, also reduces the angle of attack. So CL also decreasing. Is that clear? What is he doing? What are you doing? Is that clear? This concept? So even though if you keep your wing at 8 degree, because of the downwash, we may get only, for example, 5 degree. Okay. For our view, it will be like wing is at 8 degree. But originally, due to the deflection of flow, the effective angle will be only 5 degree. So we are calling this as alpha effective. Okay. And this much is the loss. Okay. This angle we are calling as induced angle of attack. Okay. So originally it is alpha, wing is at alpha. Due to the downwash, this is the angle we are getting. This is the effective angle we are getting. And the loss in angle is alpha A. Is that clear? This angle of attack diagram. So even though if you keep your wing at 8 degree, we will get only 5 degree. 3 degree will be lost due to the downwash. So CL is decreasing. And from this angle of attack, so diagram, we can write alpha is equal to alpha effective plus alpha I. Okay. Alpha is equal to alpha effective plus alpha I. This is one basic equation. Then with that I will finish it. And another one equation, downwash equation. So already we discussed previously, the flow velocity is horizontal. Now due to the downwash, the velocity, the flow is deflected. Okay, and the loss in angle is alpha I. Then from this right angle triangle, we can write tan alpha is equal to Wi by V infinity. And we assume aerofoil is thin, angle of attack is very small. Then angle of attack itself very small, then this alpha I also will be very, very small. Then we can write tan alpha is equal to alpha I. As the alpha I, everything is small. Instead of tan alpha I can write alpha I is equal to W by V infinity. So these two formula we will use it for the derivation. Alpha is equal to alpha effective plus alpha I. Another one is alpha I is equal to Wi by V infinity.